the system. Very simple problem. Now, notice that nothing is reaching in and moving anything. In other words, nobody is reaching in and pushing the mass. The mass is already moving at state 1. The mass is already moving at state 1. So nobody's reaching in and pushing anything. No work is being done. No work is being transferred across the system boundary. So work is going to be equal to 0 from state 1 to state 2, okay? What about the potential energy term? Delta PE. Let's start on the right-hand side. Potential energy has to do with the height of the system. It's work against gravity. Well, I don't see any height change here. It's just a table and a piece of material is moved. A mass is moved from the left to the right and stopped. There's no change in height going on. So this term here is 0, okay? So delta PE is 0. That whole term is 0, the whole term. The whole term is 0. So let's write what I got. I got 0 equals delta KE from state 1 to state 2, which is KE2 minus KE1, okay? Now, kinetic energy is 1/2 mv squared. So the kinetic energy, so what's got kinetic energy in the system? It's the mass that has kinetic energy. So at state 1, the kinetic energy is only with the moving mass. So I have 1/2 m velocity 1 squared. So the mass here is the only thing that's moving in the system. So the kinetic energy of the system at state 1 is equal to the kinetic energy of the mass, which is 1/2 velocity 1 squared. Any kinetic energy in state 2? The mass isn't moving and the table isn't moving. I guess we're assuming the table's not moving. So no, there's no kinetic energy in state 2. Everything has stopped moving. Let's write down what we've got. We've applied conservation of mechanical energy to a very simple system. And let's write what I got. I got 0 is equal to, I guess I'll go out here. I think I can do the whole thing. There we go. I'll zoom back in just a moment so you can see. So I have 0 on the left is equal to minus KE1. I got 0 is equal to minus KE1, which is minus 1/2 mass velocity 1 squared. Okay? Now, velocity 1. What the world is velocity 1? It's greater than 0. So the mass is moving from left to right. So velocity 1 is positive, greater than 0. But this equation says that all this has got to be equal to 0. The mass isn't 0. So this implies velocity 1 has to equal 0. What? Velocity 1 has to be equal to 0 according to conservation of energy, mechanical energy. That's not right. That's not right. No, the mass starts off at positive velocity. It's not equal to 0. So we have a contradiction. contradiction. Oops. Diction. Contradiction. We assume conservation of mechanical energy, applied it to a very simple situation, and it fails. It fails, big time. What is wrong? What is wrong? Well, let's go back to our simple situation here. At state one, we measure the temperature of the table and the mass. And we find that it's got a temperature T1. Maybe it's room temperature, who knows? And then, once the mass stops, I again take the temperature of the table mass system. I stick a thermometer right here, and I find out that the temperature has gone up. I have a temperature T2, which is greater than T1. In other words, the table mass system gets warmer. Table mass system warms up. Table mass system warms up. In other words, T2 is greater than T1, okay? So what this means is there's some kind of energy that is associated with temperature. We're missing some kind of energy that isn't kinetic, it isn't potential, it's an internal energy. It's energy that is stored in the mass of the system, and it's got something to do with temperature. So let's rewrite our conservation of energy equation. Let's rewrite conservation of energy. So we're missing some energy. Missing a form of energy. And we're going to call this new form of energy internal energy. Internal energy. Internal energy. And it's going to have a symbol U, and it is a function of temperature and maybe some other stuff. Function of temp. Function of temperature. I can't read that. Function of temperature and maybe some other stuff. We'll talk about that later. So let's write our new energy balance. Work equals change in kinetic plus change in potential plus change in internal energy U. Internal energy U. We got a new term, a new kind of energy, Q, U, new kind of energy, internal energy, all right? And it's got to do with temperature, something to do with temperature. Simple experiment shows us that has to be the case, okay? I think, tell you what, I'm gonna, just so we don't have a break here, I'm just gonna write delta U. That looks better, delta U. So this guy is the change in internal energy. Change in internal energy, okay? Change in internal energy. Delta, that's what the delta refers to in that equation, okay? All right, guess what? This equation is better, but it's still got problems. Still got problems. Let's see what these problems are. Let's see what these problems are. We'll again do a very simple system. We'll do a process involving a very simple system. Let's say we have two bars. So this is state one again. And we have two bars, and they are in thermal contact with each other. So we got two bars, and they're in contact, physical or thermal, if you like, contact. We got bar A and bar B. Bar A is hot and has a temperature. I guess I'll move this stuff around. A, and it is hot. And it's got a temperature at state 1, T sub A1. At state 1, the top bar is hot and the bottom bar is cold. And they are contacting each other. So B is cold, and at state 1, or time 1 if you like, TB1. So the bottom bar has temperature TB1. And remember, this is the hot one and this is the cold one. So what we're saying is TA at state 1 is greater than TB at state 1. Okay, this guy's hot. Bar A is hot. Okay? Now, what's going to happen if we sit around and wait for these bars to do their thing over time? Let's say we wait a long time. These bars are contacting each other. They're in thermal contact with each other. We got a hot bar, we got a cold bar. What's going to happen? Well, what's going to happen is the hot bar is going to cool down and the cold bar is going to heat up. And they will come to some mutual temperature. So at state 2, here's our two bars. A, temperature TA at state 2, and then we have bar B at temperature TB state 2, and they're both going to be warm. They're both going to be warm. The hot bar will get cooler, and the cool bar will get warmer. And this will happen, and what we'll find is the temperatures of the bars will be the same at state 2, the final state. So TA2 will be equal to TB2. Same temp. Same temp. Hot bar, cold bar, you wait long enough, they're in physical contact, or thermal contact with each other, and they become the same temperature over time, okay? Now, let's apply our energy balance over here. Let's apply our energy balance. This guy, the one that's modified with the internal energy term. We know we had to add it to take into account a simple situation involving friction, the sliding mass on the table. So we have this internal energy term. Let's apply this equation to a piece or one of our blocks. Let's make this our system, just one of the blocks. Let's make A our system. Okay? Let's make A our system. I could do it with B, but I'm going to do it with A. The result's going to be the same. Let's apply the energy balance. Work from state 1 to state 2, and this is for the A bar system, the one that was originally hot and becomes warm. Let's see here, is equal to change in kinetic from 1 to 2, plus change in potential energy 1 to 2, plus change in internal energy 1 to 2. Now, nothing is reaching in and pushing on any of these bars, including A. Nothing's shaking it around, nothing's moving it, so there's no work going on. No work, so that's gone. The bar is not moving, neither of them are moving, they don't speed up or slow down. There's no indication that these bars are moving or they're changing velocity, so there's no